Okay, good morning everybody. My name is Beatriz Noeda. As a member of the Oxide thin film community, I cannot be happier to be chairing together with Eckhard Salje this first plenary session of this conference with two of the biggest leading scientists in this field of oxide thin films. If someone would have told you 10 years ago that there is a ferroelectric that becomes better and better as it gets smaller and smaller, probably none of you had believed it. And the NAMLab team, led by Uwe Schroeder, has been collecting such a vast amount of evidence that this is indeed the case with hafnium-based thin films that the ferroelectric community has to listen. And now, a few years forward, many of us are hooked and convinced that indeed hafnia is the ferroelectric of the future. So this is a great example of solid and exquisite teamwork, and I am very happy and looking forward to what Uwe Schroeder has come to share with us about the devices, new devices and future devices with hafnia-based materials. Please come to stage.
Yeah, thank you, Beatrice, for the very kind introduction. I'm really happy to be here, and thank the organizers, Paul and Dragan, for inviting me to this really nice location here. And yes, hafnium oxide. I mean, 13 years ago, we never thought about this, that hafnium oxide would be ferroelectric. And now I have here a couple of topics mentioned, and Paul convinced me to add more and more to it, and I hope I can finish everything in time so that I can show you the nice properties of the hafnium oxide. This would all not be possible without collaborations worldwide and with different partners. And in the beginning we had to convince everybody to show that hafnium oxide is ferroelectric, and later on with the help of partners to look into all the devices, so the ranging here from Seoul, Tokyo, Nebraska, Dresden, Munich, NC State, Oak Ridge, and for the device applications, we mainly work together with Global Foundries in Dresden, Fraunhofer, and FMC as the companies looking into the topic. Okay, so what will be the outline of the talk? So I'll start with the discovery to show you a little bit how in the very beginning we looked into the hafnium oxide. I'll show you a little bit on the properties, and then the main part of the talk will be on the novel device applications ranging from the capacitor to the transistor, and then the neuromorphic and the negative capacitance application for the topic. How did everything start? So at that time I was working for a DRAM company in Germany with Kim Wonder. And well, we looked into a paper which, well, DRAM company looking for high K dielectrics, and we wanted to optimize the dielectric constant of hafnium oxide by adding dopants to it. And there was a paper from University of Tokyo from Tsuyomi's group over there in 2006, which basically showed that if you add a little bit silicon into the hafnium oxide, there will be like in the range here of 5 to 10%, there was a maximum of the dielectric constant in the material, and we said, oh, this looks interesting. We just wanted to look at this a little bit closer. And in the first publication here already mentioned that it's hard to distinguish the typical phases which you can get for the hafnium oxide, the cubic, the tetragonal, and the orthorhombic phase of the material. Okay, and then this is the original slide from Kimonda at that time, what we showed our management. So we basically copied the results from Tokyo. Here's the dielectric constant and the silicon content in hafnium oxide. And for the pure hafnium oxide, so in the DRAM case, well, you look into capacitance versus voltage measurements, and you just want to check yet have a linear behavior of the material. And you can see it was very flat. That's what we expected. And then suddenly, like a small bump showed up here, and then two, and then it disappeared again. And this was at the maximum of the dielectric constant. And so there was my PhD student at that time, Tim Böschke, who came up with the idea maybe it's ferroelectric, and so at that time we had a collaboration with Professor Waser's group in Aachen, and Uli Böttger there looked into the topic and said, well, let's go through a long list of things we need to prove to make sure that if this is ferroelectric, that we can prove the ferroelectricity. So we went through well, how the hysteresis looks like, the correlation between capacitance and hysteresis curve, went through subloop, fatigue, imprint behavior, piezo response, and in the end we were in the end we were convinced that the material could be ferroelectric. And this was basically from the timeline point of view. I mean, we first found this at Qimonda. Then at Qimonda, when we showed this to management, they're mainly interested into memory applications, and we used this directly into a FeFET transistor, showed on 65 nanometer ground with already nice properties, with a nice memory window in 2008. Then the company went bankrupt in 2009, and I changed over to NumLab, and we copied all the work at Global Foundries, then in 2012, and in between in 2011 we were allowed to publish the results, and this is then how the strong increase in number of applications started in the last couple of years, ranging from tunnel junctions, negative capacitance FETs to synaptic devices, piezo and pyroelectric devices, so a long list of things, and I hope I can show you a little bit of these devices during my talk. Okay, first the properties, as mentioned. 10 years ago, everybody was just thinking of these main two phases for thin hafnium oxide films, was the monoclinic phase for pure hafnium oxide, here for pure hafnium oxide, and if you added more and more dopants, then typically this tetracubic phase showed up, and both were centrosymmetric, and you wouldn't expect any ferroelectric properties in the layer. And then we kind of showed that at the interface between these two phases, the orthorhombic phase, which is a non-centrosymmetric phase, you would have here the 4 oxygen atoms within the hafnium lattice being responsible for the 2 polarization orientations of the material. Okay, let's have a closer look into this. Here's remnant polarization, the electric constant, and the phase content as looked into by Rietveld refinement of the XRD pattern. And here's the pure hafnium oxide, the monoclinic phase, and as mentioned, no hysteresis loop. Then if you increase the silicon content in hafnium oxide, you had this nice hysteresis shape for the orthorhombic phase of the material. And then kind of in between the orthorhombic and the terminal phase, this pinched hysteresis loop, which looked like anti-ferroelectric, and we're still in discussion what we really can see here. And then once you really completely tetragonal, then all the properties disappear again. Okay, and this would be was shown for all different kinds of dopants here, from silicon to aluminum to which were smaller than the hafnium oxide, to dopants which were larger than hafnium oxide. You can always see there was a certain range where you get the ferroelectric properties of the material, and with increasing atomic radius of the dopant, you could also see that the process window was increased for the larger dopants here, for example, like lanthanum case. And this is the system most people currently looking into is the hafnium zirconium system. Again, you would have in between the monoclinic hafnium oxide and the zirconium oxide a region where you see the ferroelectric properties of the hafnium zirconium oxide here, and this is about 50% hafnium and zirconium, where you see the highest remnant polarization value. From the structural point of view, most of people are looking into the material in capacitor structures with 2 tinitride electrodes, and would be here the two tinitride electrodes, and in between the hafnium oxide. And what you typically see if the tinitride grains are in the order of 10 nanometer, that the hafnium oxide shows grains which in the horizontal direction is the thickness of the material, and the lateral direction about 20 to 30 nanometers. So we have a polycrystalline material, which means that we have also typically a random orientation of our polarization direction, and with this also impact on the ferroelectric properties of the material. There are some regions where you see some orientational alignment between the hafnium oxide and the tinitride, and if you have a closer look, you can see this here. So it seems like if we have nucleation of the tinitride, which is typically deposited in the amorphous state on a crystalline tinitride, that we see in some regions these epitaxial alignment to the substrate. From the phase point of view, we had some discussions in the very beginning, what's the phase of the hafnium oxide, and here's some work from NC State. Dr. Zhang looked into this by electron beam diffraction by CBET. You take the electron beam of the TM and look at the diffraction pattern, and this is the experimental result, and you compare this. So he simulated basically for all the known structures for hafnium oxide the according pattern, and the best correlation was found then for this PCA21 or PBC21 phase of the material. And if you look now in literature, there are also the Romero phase shown for epitaxial grown films of hafnium oxide. PFM, as you heard in the beginning, I mean, there are lots of people doing PFM. I mean, PFM was very critical in the beginning, and still you have to make sure that you measure the right properties of the hafnium oxide, since like from Oak Ridge, we've seen results where even amorphous hafnium oxide shows a nice hysteresis loop. But if you make sure that you have the right measurement procedure, you can also be sure, I guess, that you find the ferroelectric properties are not just charging of the interfacial layers. Here's some work from Alexei Gruberman's group in Nebraska, and you can see here if you apply like a 4-volt pulse to the capacitor structure, you can switch from one to the other polarization direction, and from this you get the domain velocity in the material, and also the nucleation limited switching behavior as a switching behavior for these polycrystalline hafnium oxide films. That's all kind of what's expected. I mean, you have a thin film with lots of defects, and similar to the PZT case, you would have you expect kind of nucleation limited switching behavior in the material. Okay, with this short introduction to the material, I'd like to come to the devices. The first one will be the simple capacitor structure. First comparison between the material which is mainly used currently in production would be the PZT case. Here in the perovskite structure, you have the center atom defining the polarization orientation. In the hafnium oxide, as mentioned, the 4 oxygen atoms. And what's mainly similar to both materials is they have a very similar Raman polarization value, both in the order of 20 to 30 microcoulombs per square centimeter. They have a high Curie temperature. What you need for the material to, if you want to use this in a memory application, of course, you want to have good retention at room temperature. And now to the differences of both. They both have about a factor of 10 different dielectric constant. And with this dielectric constant, you would expect also just from the Landau theory that the coercive field of the material is about a factor of 10 different. And that's what you can see here. So here we're in the order of 300 to 800 versus 30 to 40 for the dielectric constant, and accordingly the field you need for switching would be here also a factor of 10 different. And from the scaling point of view, typically PZT was used in capacitor structures down to 70 nanometer, and then an issue started with interfacial layers, depolarization fields, and for the hafnium oxide, ferroelectric properties were shown down to the 5 nanometer and below, even 3 to 2 nanometer range for the material. Switching kinetics. I mean, this is important for further applications of the capacitors. As we've seen already from the PZT case, we have nucleation-limited switching behavior for the hafnium oxide. In the epitaxial PZT, we typically have the chi switching behavior, and for the polycrystalline PZT, then also nucleation-limited switching behavior. So it all depends probably to the number of defects in the interface, how your nucleation starts and grown from one to the other polarization orientation. And you can see this also, I mean, for the nucleation-limited switching behavior, would expect 1 over T versus 1 over E squared behavior for PZT, and it's very similar for the hafnium oxide compared to the PZT case, and in both cases, you can see pretty much linear behavior, and the only main difference would be here, as expected for the coercive field, the different field values for the material. Field cycling behavior in the capacitor structure. In the PZT case, it was important to have oxide-based electrodes for that PZT to get really stable field cycling behavior, to get a constant Raman polarization value over field cycling here, and not fatigue behavior as visible here for platinum electrodes. Similar for the hafnium oxide, if you optimize your material, you get also quite stable field cycling behavior with almost no wake-up effect, but the field cycling typically drops in the order of 10 to 8 to 10 to 9 cycles due to fatigue of the material. And currently, best values reached are in the order of 5 times 10 to 10. This is work from Moscow on lanthanum-doped hafnium zirconium oxide. Retention and imprint. As you can expect, I mean, I mentioned the 2 different coercive fields. For PZT, it was a little more critical due to the low coercive field to get good retention values. For the hafnium oxide, this is not that critical, and you can see, I mean, typically samples are polarized in one direction, then heated up, in this case here to 125 degrees C, and then you look at the polarization or the opposite polarization of the material and check how stable retention is. And you can see for same state polarization that it's quite stable, and you see a drop here for the opposite state retention. And this is not coming from that you really get a depolarization and a drop in Raman polarization. It's just coming from, as you can see here, a shift of the hysteresis loop. And this is mainly due to charge induction into the interfacial layer. And overall, if you think of your hafnium oxide, which is the order of 10 nanometer, and if you have possibly interfacial layers in the order of 1 nanometer, there's a strong field to inject charges into this interfacial layer, which are leading to this shift of the hysteresis loop. And this is also, if you look at the comparison here for the depolarization field for the PZT versus the hafnium oxide case, the behavior is very similar for both. It's just that they both run in different thickness ranges. I mean, the PZT is typically in this 70 and above 100 nanometer range, and the hafnium oxide in this 10 nanometer range. And here, the depolarization field is about a factor of 4 higher compared to the PZT case. You would expect also a stronger injection of charges. And Alexei Gruverman's group will show tomorrow in the afternoon some more work on this imprint behavior. Okay, so this was the first device. The second device would be the transistor. And basically what we do, we took GlobalFoundries transistor, which is a high-performance transistor, for the newest chip generations, and in this case it was, just to make it more simple, a planar transistor, 28 nanometer ground rule, and depending on the polarization, well, basically we just, in the high performance transistor you have like 2 nanometer of hafnium oxide in between a tinitride and your silicon substrate with a thin silicon oxide interfacial layer. You replace this 2 nanometer hafnium oxide by 8 to 10 nanometer of ferroelectric hafnium oxide. And then the polarization within the hafnium oxide would impact, of course, your channel region. You would have a different charging of your channel region, and depending on your channel region, you would have a different turn-on voltage of your transistor. I mean, there's which is called threshold voltage, so you would see a threshold voltage shift here for the one to the other polarization state, and this is the current you measure here on the drain. And the voltage would be here applied to the top of the transistor structure. So you can see here we have our memory window here between the two different polarization directions of hafnium oxide. With this, you can use this as a memory device. You basically look at a certain voltage, for example, and look at the current and can check without disturbing the polarization state of the material and measuring the polarization orientation. And Global Foundry did this on 300 millimeter wafers together with Fraunhofer here, and showed that on 300 millimeter wafers you form this nice transistor structure, and you have a good memory window, so the green color would be a memory window above 1 volt, nicely on a whole 300 millimeter wafers for all transistor structures, and you have a clear separation for the two threshold voltages for all the structures. So overall, from the FeFETS feature point of view, we have polycrystalline hafnium oxide, memory window of 1 volt, retention larger than 10 years, and endurance in the order of, so you can cycle it up to 10 to 4, 10 to 5 times. And then again, you get, similar to what I showed for the capacitor case, charge injection into your interfacial layer, and this charge injection would shift your threshold voltage so that the memory window closes. So the device doesn't break, it's just a shift, and you can detrap your device and it would work again. The overall advantages would be it's fully CMOS compatible, highly scalable compared to like your USB stick where you need like 18 volts. Here you're in the 5 volt range, so you have a much lower voltage you apply for switching, and you have fast access time. So now let's have a look how small and larger devices behave. If you have a large FeFET, and you can imagine, I mean, you have all your hafnium oxide grains in your transistor structure, and basically let's think of one grain as one domain. This is the simplest approach. You can imagine, I mean, we have all the different orientations of our grains, and we have slightly different sizes of these grains, so we would expect slightly different coercive voltages for each grain, which means that they all have a different voltage where they switch. That's what you can see here. I mean, these transistor devices are 100 micrometer in width, and you need to apply a voltage here ranging from like 3 to 5 volt until you really completely switch all your domains within the transistor and switch from one to the other threshold voltage. But if you now scale your devices to smaller and smaller structures, and here in this case it's a 30 nanometer times 80 nanometer structure, and if you remember the TM image in the beginning, I mean, this is about 1, 2, 3 grains in the transistor structure. We see here very abrupt switching between the two polarization states. And now, well, we looked in different devices. So there were some devices where you have like 3 times switching, and overall you can explain then everything if you would have a transistor structure where you have 3 grains in the structure, and then by applying higher and higher voltage, you can first switch the first domain, then the second, and then the third domain till you completely switched all your domains within the transistor structure and switch to the other threshold voltage. And now you can do a little bit statistics on it. And if, for example, if you look at 1 voltage and you do this 10 times, you can see that every time it would behave a little bit different. You can get the switching probability, and overall you see that switching is a stochastic process, and you have a Poisson distribution for all these switching events happening. And again, we can look for the different voltages here, and you can see again we have nucleation limited switching behavior, so 1 over v square behavior for the switching event. So independent, if we look with the PFM, we look in the capacitor structure or in the transistor structure in all times, as expected, we would get this nucleation limited switching behavior. So now, if you think, well, this seems very clear, and now you look into, I mean, if you have like 1 pulse with a certain pulse length you apply to your surface, what's happening if your pulse is below the coercive field? And you would expect, well, it wouldn't switch, I mean, if your pulse time is short enough. And, well, so if 1 pulse doesn't do it, what's happening if you do multiple pulses for this voltage below coercive field? And you can see, I mean, in this case here, it's all work here from Halut Manovic, and he basically had here 10 pulses before he had the switching event, and you switch from one to the other polarization again, and same again for the other direction where you can switch back your device. And well, how can you explain? I mean, especially if you knew in the beginning that you had nucleation limited switching behavior for the material, then you can also imagine, I mean, that you have to form first some nuclei in the material, and then if there's a certain number of nuclei, then you have the complete switching behavior. And if you would have these subthreshold voltage nucleation, that you need a certain number, and then certain number of these, then you would have the complete switching event happening. And you can do this for a lot of different voltages, and you can see that there's an extremely strong voltage time dependent of the switching behavior. So like here at 1.6 volt, you would need 10,000 of these small pulses, and you still get switching behavior for your transistor, versus in the case of 2.2 volt, you would have only 1 pulse and nice switching. And the opposite can also happen if you just change the time and the same voltage. So for a short time, you would need also a certain number of pulses, versus for a longer time, you would have it in 1 pulse. Okay, so this is already all what we need for the neuromorphic application now. And before I come to detail in how this would work, I need to explain you a little bit how a human brain works and what's the main difference between a current computer and the human brain. As you all know, I mean, in our computer, we take the data which is stored either in a hard drive or a USB stick or a DRAM. We have to transfer the data to the CPU for calculation, and then we move back all the data to store the data again. And the human brain is completely different. Basically, you have 2 main things. It's a synapse and a neuron. These are the 2 parts of the brain. You have a connection between lots of these neurons in the brain. And the computing in the brain works completely different. I mean, in the brain you have, basically the synapse, which has some memory storage options, but on the other hand, since it's the connection between the neurons, there's also some, I mean, it's basically based on the storage of the information awaited and distributed computation of this information within the brain. And the neuron basically does just some integration operation. So there are some spikes coming from all different neurons in the brain, and depending on the spiking within the brain, you get the overall operation of the brain. So, and in this talk I will mainly focus on this spike-based, brain-inspired neuromorphic application, and like to show you how you can use your FeFETS structure to do this. And the main interesting thing, and that's why people are looking into this, is compared to a computer where, you know, there's a lot of heat generated, our human brain is much more low power, low space, and high speed operation compared to what you have in your computer. Okay, first part would be the neuron. As mentioned, I mean, there are lots of different neurons around one neuron, and the synapse kind of transfers the information from all different neurons, and then the neuron does this some integration of all the spikes coming from all different kind of synapses from all around. And then depending on a different threshold, there's a firing event. So there's an output signal coming from your neuron, and then there's a rest time for the neuron, typically in the millisecond range, and after this rest time, you would have the next, some integration event. And as we've seen already before for the FeFET, I mean, there's a very similar behavior for the FeFET. If we have spikes, basically if we have our pulses coming for the FeFET, then at some certain number of these pulses we have the switching from one to the other polarization state. This would be our firing event. And the very nice thing about the FeFET is you can have this also the opposite direction. So basically, you can imagine, I mean, something like this works also in your eye. And well, I showed you before that for different voltages you need different number of pulses before you have your firing event. And you can imagine in your eye, for example, if you look in the dark, it's very hard to see something, so there would be a low number and low voltage basically of your spikes. And if you have more light, everything becomes much sharper and there's a much better communication between the neurons in the brain. So these are basically like these two cases, what you can see here. In one case, voltage is lower, a larger distance between spikes, and in the other case, there's much more spiking, so there's a much better connection and interaction between the neurons in your brain. Okay, so this would be the neuron, and the second one would be the synapse. In the synapse case, we're looking now, I mean, the neuron was the small FeFET, and in the synapse case, we take the large FeFETs where we have lots of different domains within the transistor structure, and then depending on the voltage you apply here on the top electrode, we have a different gradual switching from one to the other polarization orientation. And so as I showed before, I mean, depending on the voltage you apply, you have just a partial switching and a partial change in VT. And this could be in both directions, and in the brain this is called potentiation or depression. And this could be also done by different timings, what you have here. And basically how it's done in the FeFET case now is you take this FeFET, and we have the pre-neuron and the post-neuron, and it depends on the timing between these two, what's happening in your transistor. And that's what I like to explain you over here. So if there's the pre-spike is a little bit earlier than the post-spike, and so the information would cause a voltage in positive direction on your FeFET structure, which means depending on the timing, first of all, you have a certain switching of your polarization state in the FeFET, plus there's a different voltage. So you have two operations at the same time, and that's very similar to the brain. And you can have the opposite case. So this would be here the different timings, and this is voltage or the charge on your device. And you could have the opposite case. If the post-spike is a bit earlier than the pre-spike, you would have a negative voltage on your overall structure. So with this, basically, the synapse and the neuron could be realized by one FeFET, and the only difference of the two would be that you use a larger or smaller transistor for this application. Okay, so now coming to the final topic is negative capacitance. And this topic was introduced in 2008. Salahuddin and Datta wrote a paper. So the main topic for high-performance transistors is, again, as I mentioned before, high power consumption. And there's a lot of people working on how to reduce the power in the devices. And one idea was if you increase the subthreshold slope, basically the turn-on slope of this transistor here, again, drain current versus the voltage you apply to your transistor structure. And there's basically a Boltzmann limit on what the maximum subthreshold slope is. And the idea was if you can introduce some kind of negative capacitance in your transistor structure, that this would improve your subthreshold slope. And, well, the main discussion was always, well, if I shrink down my thickness of the hafnium oxide down to what's currently in high-performance transistors in this 2-3 nanometer range, that it's really unclear if you really have ferroelectric properties, and there are PFM studies done on the topic, but still the discussion was ongoing. Do you really see a negative capacitance effect? So we looked into the topic and wanted to prove this kind of that this is possible. And just to explain you where the basic idea is coming from, if you think of the Landau theory, then you would have, for the Gibbs free energy, this double well potential, and coming from one to the other polarization state, you have to overcome this barrier here. And important part would be this region where you cross your barrier. So if you derive your structure, you would have this E versus polarization, the field versus polarization characteristics. You just flip E and P, you get to this known shape. And typically, if you look in the structure, the slope of this curve would determine the capacitance of the material. And of course, then you would go from a positive capacitance through a negative differential capacitance region, again, to a positive capacitance. And if you typically measure your capacitor structure, you won't see this, because you typically, what you do is from here to here, you would directly switch from one to the other polarization orientation. You wouldn't go through this whole S-shaped curve. And the idea from Salahuddin and Datta at that time was, if you now combine a dielectric capacitor and a ferroelectric capacitor, add the two, and then you would get to this more what they sort of stabilized negative capacitance region for this two capacitors in series. And our idea was now, and Michael Hoffmann was working on the topic, to go through a series of capacitor structures with a different thickness, and that at some point in time we should see this effect. And basically, if you have your structure, you can imagine that in some point, if there's a negative capacitance and you measure the charge on your overall structure, that at some point in time there should be a change in the charge measured on the overall system, and that's what you can see here. There's a small kink here, and if you calculate from the charge versus voltage to the polarization versus the field, you would follow kind of a S-shaped curve. And the very interesting thing was that there's also no hysteresis effect. And this is only happening if you do the switching fast enough. I mean, it needs to be fast enough that there's no charge trapping into interfacial layers to a complete screening of your dipole. And he could do this for tantalum oxide and aluminum oxide case. And from this S-shaped curve, you can calculate then back, as I showed you in the beginning, the double well potential of your ferroelectric material. And well, the thing is, if you now look at device conferences, there will be tons. I mean, there will be a lot of sessions on these negative capacitance effects, and the critical thing, I mean, coming from the material point of view, is really looking to, are these 2 nanometer films they're putting into the device structures, are they really ferroelectric? With your knowledge, it's typically easy to see. And the other thing is, from the device point of view, that you have a hysteresis-free switching behavior, because if you would have a hysteresis, you wouldn't be able to use your transistor in the normal operation mode. So with this, the end of my talk, I'd like to quickly summarize. I hope I could show you the ferroelectric properties in hafnium oxide, and I showed you only one part of the root courses. There are more than just the dopants to form the ferroelectric properties. There's a longer list of different devices you can build with the hafnium oxide. And looking into the FeFETS, I hope I could show you that the large FeFETS have a gradual switching, and then with this gradual switching are nicely to be used for the synapse case, versus the small devices have abrupt switching, and for this we can use this for the neurons. Then I could show you that we verified the negative capacitance behavior in the FeFET structure. But looking at the FeFET overall, the main challenges are the low endurance currently, and here one needs to be something to improve the defects, I guess, in the film, to improve the limited endurance behavior we have, and this is mainly caused by charge trapping. So I'd like to thank you for your attention. I'd like to thank our funding partners. I thank all of our partners helping us on the topic, and could be probably even longer list of people who helped us working on the topic than the team at NAMLab working on FeFETS. And if you're more interested in hafnium oxide, there are 2 sessions today and tomorrow just on hafnium oxide, and also a book just came out on the topic. Thank you very much.
Thank you very much for sharing with us these exciting results. We have 1 or 2 minutes for questions. Yes. Microphone here. Excuse me.
Okay, I can shout.
No, I don't think so.
I can't shout. Okay.
I think
Thank you, Paul. Thank you very much. Brilliant talk. So the neuromorphic computational side is, of course, very interesting. So the brain, I understand, is totally athermal. So all your relationships you have shown should be sort of parallel relationship, and that's not compatible with Abrami, Ishibashi. So you showed some data which on a log were linear, but some were exponential. And I'm slightly worried about the exponential ones. I mean, did I get that wrong from your pictures? I mean, do you have predominance of power law dependencies, or do you have sort of exponential time dependencies and so forth? I mean, you had one graph where you showed both in this on the same slide. So
on one slide I wanted to just show the comparison between, I guess this was one slide, hafnium and Piezo T case, and it was more every time we have the polycrystalline material, we have the nucleation limited switching behavior, and the Chi case was for the epitaxial Piezo T case. So the thing I wanted to mention, as long as we have the polycrystalline material and it's the same in Piezo T and in hafnium oxide, that they both showed nucleation-limited switching behavior for the material, and they both have this 1/T versus 1/V square behavior. And we see currently only differences. Well, we kind of RC limited in some of our capacitor structures, and then we have, depending on RC delays, then some
do you have a massive temperature dependence on the hafnium oxide?
Well, I showed this also on one slide for the transistor case. It's very similar what Tangantsev showed in his paper, how this behavior should behave with temperature, and it's all according to classical nucleation-limited switching behavior. And that's very important for this neuromorphic application, yeah.
Of course. Thank you.
Yes, I see a question there. Manuel?
Okay, thank you very much for this very nice talk. So the devices that you showed us seems to be quite advanced. So I was just wondering which one is closest to going to market.
That's a good question. So I mean, if you look at the behavior of the devices, I mean, if you look at your USB stick, there you have also only the possibility to switch it between the two different memory states like 10,000 times. So that's very similar to the 10 to 4, 10 to 5 cycles we showed for the FeFET case. On the other hand, there's one thing you have to, and that's one of the discussions we're currently having. And if I showed this sub-threshold voltage switching behavior we use for the neuromorphic application, if you think of an array of 1 transistor memory cells in the array, this would mean, I mean, if you're like trying to switch one memory in the whole array, you have to apply certain voltages. And the problem currently we have is like a disturb issue that if you want to switch one device here, you have a little bit sub-threshold switching for another device, and this is kind of limiting then the behavior in a complete array. So I think the FeFET array is a little bit critical. I would probably vote for the 1T, 1C cell, because in this case you have an access transistor which avoids that there's any gradual switching of your capacitor structures. And as I showed, I mean, so far we have 10 to 10, 10 to 11 cycles and the imprint, and so we have to improve a little bit on the defects within the hafnium oxide to further improve the field cycling behavior. But overall, I think, I mean, if you look at the Piezo T case, it took also like 10 years to get something in production, and we just started like 10 years with everything so far.
Okay, thanks.
Okay, in view of time, we have to stop here. We thank the two speakers of this plenary session, Uwe Schroeder and Jean-Marc Tuscone, for their contributions.
Thank you.